Question 7. The following diagram shows part of the graph of the quadratic function f. The graph of f has its vertex at 3, 4, and it passes through point Q as shown. Part A asks, write down the axis of symmetry. All right, I'm going to note this is only 1 mark, so there's no calculation really needed for this. Okay, so the axis of symmetry, the formula for this is in your formula booklet, though we don't actually have the function for f, so we can't actually use the formula for this. So it's always in the form of x is equal to a number, and that number is going to be the x value, or the line that sort of cuts our quadratic function or parabola in half. Okay, and so if we think here, if we've been given the vertex, if we have that vertical line coming through here, that's going to sort of cut our parabola in half, and it goes directly through the x value of the vertex. All right, so this is quite simply x is equal to 3. All right, and so yeah, that is the answer to part A. Let's we'll highlight this axis of symmetry. Okay, let's highlight this idea of vertex at 3, 4. All right, let's move down to part B. The function can be written in the form fx is equal to x minus h squared plus k. And part 1 asks us to write down the values of h and k, and part 2 asks us to it says point Q has coordinates 5, 12, find the value of a. All right, so what I'm going to do to answer this is we're going to, bring this down, bring question B down to a new page, and we'll attack it from there. Okay, nice, let's bring that there. And I'll just note that we have the vertex of f is 3, 4. Now this form here, fx is equal to a multiplied by x minus h squared plus k, is known as vertex form. Okay, where the vertex is going to be, you can think about it is going to be the value of x that makes this bracket here equal to 0. All right, and then k will be the y value. All right, where you can sort of wrap your head around it a little bit, I suppose, is the x minus h squared, so an expression squared, is always going to be more than 0. Okay, oh, that's the wrong way around. I meant to do it like that. It's always going to be more than 0. Okay, so the smallest value it can take is 0, and then so therefore the smallest value that this fx can take is going to be 0 plus k. All right, so if we find the value of x that makes the bracket equal to 0, then k will be the y value and will be the minimum point, or the vertex. All right, so without further ado, let's go through this. And so therefore, because this is in vertex form and we're given the vertex, all right, this is h is going to equal 3 and k is going to equal 4. All right, and so yeah, that's the answer to part B I, or part B1. Moving on to part 2. All right, we are told that point Q has coordinates of 5, 12. All right, and now we got to find the value of a. All right, so now what we're going to do is plug in x is equal to 5 into fx, or well, we know that f of 5, or when we plug in x is equal to 5 into our function f, the value should be 12 at the end. So what we're going to do is, let's say there's sub x is equal to 5 into fx, and f of 5 is equal to 12. All right, and so then if we do this, we're going to go through and we'll say that f of 5 is going to equal a. I should have written and rearranged for a up the top here, but yeah, we'll see how it works when we work through. So a multiplied by 5 minus h, which we've found here, which is 3, squared, plus k, which is 4, is going to equal 12, right? And so now we just go through a process of rearranging to find a. So first things first is, let's clean up what this is going to equal here. So this is going to be 5 minus 3, which is going to be 2, and then 2 squared is going to be 4. But let's, so this is going to equal, and actually let's go over here. We'll say 4a is going to be equal to, in fact, we will put everything in and then we'll do another line, is equal to 12. And then so now what we're going to do is try and get rid of the 4 from the left-hand side. And the way we're going to do that is just subtract 4 from each side. Okay, so from the left-hand side and the right-hand side, and that's going to give us 4a is equal to 12 minus 4, which is going to be 8. And then the next thing we're going to do is going to divide by 4. So we'll do that and divide by 4 on both sides. We'll get 4a divided by 4, which will just leave us with a. And 8 divided by 4 is 2. Okay, and so there we have the value of a. Cool, let's move on to part C. So the line L is tangent to the graph of f at Q. Find the equation of L. All right, lovely. So in order to form a line or the equation of a straight line, there are 2 ingredients. I sometimes say it's a very simple recipe. 2 ingredients. You need a point and a gradient. You need a gradient of the line and a point that the line passes through. All right, so we know the point that the line passes through. It's 5, 12. But we don't know the gradient of our line yet. Okay, so the way we're going to find the gradient is by differentiating our function f. All right, so find the first derivative, which we can also refer to as the gradient function. Then we will sub in x is equal to 5 into that gradient function, and that will give us the gradient of the line. And then we'll go through and find the value of so the equation of line L. All right, so let's do this. I think it should be all right. Yeah. So let's copy this, bring this down to here, make it a bit bigger. Yeah, that's cool. And let's just jot down what fx is going to be. So fx is equal to 2 multiplied by x minus 3 squared plus 4. Okay, so in order to differentiate this, the easiest way is going to be to expand it out and then have it as just a polynomial in terms of x, and then we'll just differentiate each term. So let's go and do that. So we'll expand out fx. And so a common error that's made when expanding out a bracket like this is to say that it's going to be saying this equals x squared plus 9, sort of just squaring both terms. Unfortunately, that's not correct. All right, so you've got to either think of it as x minus 3 multiplied by x minus 3, and then run through the FOIL idea where you do the first and then the outers and then the inners and then the last. Or if you sort of get the hang of it, you can sort of run through it this way where you sort of go, well, the first are going to be x squared, then I'm going to get 2 lots of negative 3x, which will then give me negative 6x, and then we'll get negative 3 times by negative 3 on either end, which will give me plus 9. Cool, and then we get plus 4 on the end. Now, if we clean all this up, we'll get 2x squared minus 12x plus 18, and then plus 4, which is going to give me plus 22. And then now I have an expression for fx, sort of just as a polynomial, which is going to be easier to differentiate. Now, the formula to differentiate this is in your formula booklet, But if you have an expression, let's go into purple. So if you have fx is equal to ax to the power of n, all right, and then that's actually, we'll go, then therefore f dash x is going to equal n a x to the power of n minus 1. All right, so it's sort of a two-step process. You bring the n, the power, all right, to the front, multiply that by the coefficient, and then you have to subtract 1 off the power. All right, and so yeah, and then we do that to each term along the polynomial. All right, so we'll do that here. We'll find f dash x. Okay, so with the first term, 2x squared, I'm going to bring the 2 from the power 2 to the front and multiply that by the coefficient, which is also 2, which is going to leave us with 4x. All right, and then sort of a hard and fast rule that you can remember for x to the power 1 term, or just x terms, is you just drop the x. Okay, it's pretty easy to just remember that. So yeah, we just drop the x there. So our first derivative, or gradient function, of fx is 4x minus 12. Now, in order to find the gradient of the line L, so the tangent to the graph at point Q, we're going to have to substitute the x value for point Q, which is 5, all right, into our first derivative. And then that's going to give us the gradient at this point up here, all right, which is a relatively steep gradient. And we'll see that it's, the gradient that we find is going to be relatively steep as well. Okay, so let's substitute x is equal to 5 into this. That's all right, and yeah, we'll write sub x is equal to 5 into f dash x to find the gradient of our line L, which I'm just going to represent as ml. Okay, and so we'll do that, and we're going to get, let's bring everything over as well so I don't run out of room, and we'll go f comma 5. F dash 5 is equal to, 4 multiplied by 5 minus 12, which is going to equal 20 minus 12, which will be equal to 8. All right, so then therefore the gradient of line L is going to equal 8. And so now we have, our gradient, which is great. So we have a gradient of our line L, and we have a point that it passes through, which is Q, which is 5, 12. And so there are two ways you can go. The formula that's given in your formula booklet is called the point gradient formula. You can use that, or otherwise you can sort of just use the idea of y equals mx plus c, so the standard sort of, so what do they call that? The gradient intercept form of a line. And fill in the blanks. So we have m, we've got a y value, we've got an x value, and rearrange it to find c. Both are equally fine. And I'm going to show you both ways. Okay, so I'll show you both ways here. Right, to find the equation of line L. So if we come back to the formula booklet, I'll bring over the, no, wrong way, it's down here. So this point gradient formula here, y minus 1 equals m multiplied by x minus x1. So I'll bring that over. So if we were to use that on this side, all right, and we have our L is equal to, so the gradient of M is, of L is 8, and Q is 5, 12. All right, what we do is we'll go y minus, so 12 is going to be our y1 for this formula here. We go y minus 12 is equal to 8 multiplied by x minus x1, and x1 is going to be 5 multiplied by x minus 5. Now we rearrange this to get this into the form of y equals mx plus c. Now the question hasn't actually specifically said the form in which we need to leave line in. So I generally I go back to y equals mxc as sort of my default format. And so I'd say that this is equal to y is equal to 8x minus 40 and then plus 12. So in that step, I've expanded this bracket out and I've also added 12 onto both sides. So brought 12 over to the side, and then simply here we'll go y is equal to 8x minus 28. And so there we have the equation for our line, or the tangent to the curve at Q. And if we wanted to use just the form of, y is equal to mx plus c, the way I go about this is I sort of say, well, our y value is 12. So I log 12 in for y. Our m value, or the gradient, is 8. So I log that in for m. The x value is 5. So put that in here. And plus c. And then I just rearrange this for c. So I say 12 is equal to 40 minus c. Right, and then so we can sort of say then c, therefore, c is going to equal, c is going to equal 40 minus, that's meant to be plus c. So 12 minus 40, beg your pardon, 12 minus 40, and that's going to equal negative 28, and so therefore y is equal to 8x minus 28. And so there you have it. Two ways of answering the same question. And getting the equation for line L. Okay, on to part D. What have we got? Now consider the function y equals gx. The derivative of g is given by g dash x is equal to fx minus d, where d is an element of real numbers. And part D asks us to find the values of d for which g is an increasing function. And part E, we'll do these two together, okay? Part E says find the values of x for which the graph of g is concave up. All right. Okay, cool. Let's grab these and we'll go bring it down to a new page. And that'll do. Sweet. Okay, lovely. So this g, the gradient for g, which is given by this g dash x idea, right, is given by fx minus d. Now, in order to have an increasing function, what we need is the gradient for g, or the gradient for the function, to be positive. All right, a positive gradient is an increasing function. All right, and we figured out from before that if we look at, so fx is equal to 2x minus 3 squared plus 4. So therefore, g dash x is going to equal this minus d. Okay, and in order for it to be increasing, we need this to be more than 0. Okay, and so if we go back to what we kind of briefly talked about before with this vertex form idea, this expression here, this 2 multiplied by x minus 3 squared, is either more than or equal to 0. Okay, so all right, so that's the minimum that can take is 0. The minimum value of this expression here, underlined by green, is going to be 0. And so the smallest value of, we talked about before, the vertex is going to be where x is equal to 3, or the x value that makes that bracket equal to 0, and then plus 4, the constant on the end. Now, so it could probably coming to you quite quickly here that the value of d that we need in order for g dash x to always be positive is we need D to be less than or equal, less than 4. Okay, so therefore D is less than 4. Okay, and yeah, that's the answer to part E. And yeah, we can go from there. All right, so now on to part E. Find the values of x for which the graph of G is concave up. All right, so going back to the idea of the derivative, and we look back when we found the first derivative of f, you'll notice that we didn't touch on this enough, but constants. So I won't do that in red. That's not a. We'll go in green. The constants disappear when we differentiate them. That's because they have the constant term on the end of a function has no influence on its gradient. Okay, only the terms that have x involved with them, or when x is an element of them, they can influence the gradient. Though constants literally just shift our graph or our function, or up and down the y-axis, shift it up and down. All right, so if we go back to part E, and we're seeing here, so we're going to find the values of x for which G is concave up. Now, if G dash x is going to be equal to, if G dash x is equal to, fx minus d, which we'll say is 2x minus 3 squared plus 4 minus d, or equally, we could even say, we could take our expanded version from up here, and we can copy, paste that down here, get rid of all that, 2x squared minus 12x plus 22, and then we'll also have that minus d on the end. Okay, so then, therefore, the second derivative of G dash x, is just going to equal the same as the first derivative of f, okay? Because all we've done, the only difference between the first derivative of G, or G dash x, and f dash x, or fx, is this d element, all right? So then if we were to then take the second derivative of gx, the d and everything else would just drop off, all right? The constants will just disappear. Okay, and in order to find a concave up function, or to find the value of x for which a graph is concave up, we need to find when the second derivative is more than 0. We've probably touched on that before, but here we'll say we need to find when G dash x is more than 0. All right, so then we need to find when f dash x is more than 0. And we had the expression for f dash x up above, so which is equal to, in fact, how about we put it over here? We'll add it on the end of this, which was 4x minus 12. So we need f dash x to be more than 0, which we'll put in down here as well. Let's say 4x minus 12 to be more than 0. Now we just need to rearrange this. So we need 4x to be more than 12. All right, and then we divide both sides by, so this is where I added 12 on each side. So I brought the 12 over to the other side. Now we're going to divide by 4 on each side. We're going to get x is more than 3. And there are the values of x that make our graph G concave up, or the function of the values of x for which the graph of G is concave up, I should say. And there is the answer to part E, and the full answer to question 7.